Welcome everybody to the second lecture on Waveguide. In this lecture, we'll be talking about the different types of waveguides with some analytical manipulation for the rectangular waveguide, and for the remaining kinds or types of waveguides, we'll be talking more theoretically. Rectangular waveguide is one of the earliest types of waveguide that has been used in like transporting microwave signals. They are still in use. Like many different components are based on waveguide, like couplers, detectors, isolators, and so on and so forth. But the usage of waveguide is decreasing for the favor of using what we call it like planar waveguide, like the waveguide on a printed circuit board. Why? Because it's more convenient for integration with electronics. It's less weight, less size, less cost, so on and so forth. So it's more useful. Of course, the planar transmission line or waveguide, like on the PCB, is limited mainly by the amount of power it can carry. So for any application that is high power, we'll go for like waveguide structures. For things that's like low power, of course, the preference will go for the planar or PCB waveguide. Rectangular waveguide is a hollow waveguide, so it's just a single conductor. This it doesn't carry TEM waves. It just can carry TE or TM waves. As we described last time, we can prove that the propagation of TEM wave inside a waveguide requires two conductors. And of course, like the rectangular waveguide is a single conductor, so it carries only TE and TM. So those are some shapes of different components that are based on waveguide, rectangular waveguide, like the coupler, like bend, attenuator, adjustable load, magic T, so on and so forth. So the rectangular waveguide is a uniform rectangular cross section in the XY plane. For the analysis, we'll assume it's in the XY plane, and the waveguide is extending along the Z axis. As we discussed in previous lecture about the TE mode is characterized by EZ, longitudinal electric field, equals 0. So we only have H longitudinal component. We can express it the same way that we did in the previous lecture. H of Z, which depends on X and Y, and it is propagating in the positive Z direction. And to find the fields for the TE mode, we need to like solve the homogeneous wave equation for HZ. This equation can be solved by separation of variable. Separation of variable is the method that we studied before in 303 electromagnetic fields. In separation of variables, we express H as a function in X multiplied by a function of Y. So the homogeneous wave equation will be taking this format, and we can just substitute this separation variable into the wave equation to reach this form. So the separation of variables can lead to these two separate equations where we define new variables kx and ky, such that kx squared plus ky squared equal kc squared. Kc squared is the same meaning as we discussed last time, which is the cutoff frequency. So this equation is like decomposed into these two equations, such that kx squared plus ky squared equal kc squared. Solving those equations, we'll find that the expression, the general expression, general solution for h of z, the longitudinal magnetic field, does have this expression. And in order to find the value for kx, ky, a, b, c, d, what we have is the boundary conditions. What are the boundary conditions that we have here in this case? The boundary conditions that we have in this case is that the tangential electric field equal 0, and we have tangential electric field here, Ex equals 0 at y equals 0, Ex equals 0 at y equal b, Ey equals 0 at x equal 0, Ey equals 0 at x equal a. And one more thing here, we are always assuming that a is larger than b. So we are assuming the x direction as the longer side of the rectangle. So those are the boundary conditions that we have: Ex at y equal 0 and b, Ey equals 0 at x equals 0 and a, which are the tangential electric field equals 0 at the conductor surface. So applying those boundary conditions on the expression for Hz, we can find the value for Kx and Ky to be as such, and this parameter depends on the amount of power. So like this would be like the magnitude of the signal, and those two parameters Kx and Ky shape the like configuration or the distribution of the field. So this is H of Z. To find E and H, like the tangential or like the transverse electric and magnetic field, Ex and Ey would have this expression, just substituting the wave equations that we had last time. That's not here, it's in the previous lecture. So just substituting them to find the expression for Ex, for Ey, Hx and Hy. Here the propagation constant will equal k squared minus kc squared. So k is the wave number, kc is the cutoff frequency. If k is larger than cutoff frequency, it will be like a real propagation constant. If k is less than the cutoff wave number or the cutoff frequency, cutoff wave number, beta will be imaginary, and the propagation constant would be like a propagation constant for a decaying wave. So here m and n are integers, so we define the mode by those two integers. The first one is the integer along x, along the wider dimension of the cross section, and second integer is along y, the narrower dimension of the cross section. The cutoff frequency is just like we get it from here, and it is related to m and n. Below this frequency, the mode is not propagating. Above this frequency, the mode is propagating. Okay, so the mode with the lowest cutoff frequency, today we'll introduce a large number of definitions, so you need to just grasp them. So the dominant mode is the mode with the lowest cutoff frequency, because we assume A is larger than B. The cutoff, the dominant mode will be TE10. So this is the lowest cutoff frequency. if m equal n equal 0, we'll find that E and H will be 0, and there is no modes. So there is nothing called like TE00. The wave impedance for TE is EX over HY or minus EY over HX, which will have this expression. The wave impedance is real if beta is real, or if the mode is propagating. The wave impedance is imaginary when beta is imaginary, or like cutoff mode. So the modes that are not propagating, the modes with cutoff frequency larger than the signal frequency, is called cutoff modes or evanescent mode. If more than one mode is propagating inside the waveguide, we are saying this waveguide is overmoded. If we have modes, like different modes with the same cutoff frequency, we are saying those modes are degenerate modes. So just like when you read it, you know what is the meaning of degenerate modes. The guide wavelength, lambda g, is defined as the distance between two equal phase planes along the waveguide, and it is equal to lambda 2 pi over beta, lambda g equal to pi over beta. And in general, lambda g is larger than lambda. Lambda is the wavelength in the material that's filling the waveguide. The phase velocity equal omega over beta. We'll find that the phase velocity is larger than the speed of light in the dielectric filler of the waveguide. As we discussed last time, it is the phase variation which can be larger than the speed of light, but the wave propagation velocity can't be greater than the speed of light. And also we can look here for the phase velocity. We find that it is higher than the plane wave velocity in unbounded material with the same property. The mode is dispersive. Last time we described what is dispersive. Dispersive means it's varying its velocity with frequency because of the conducting waveguide or the conducting structure. If on the same media, in unbounded media, like also like space propagation or propagation in just homogeneous medium, it is non-dispersive. But because of the metallic structure of the waveguide, the waves start to be dispersive, which means that it is depending on frequency, the velocity of the signal depending on frequency. Okay, how would we represent the field in the transverse field? We know that along the z-axis it is sinusoidal propagation along the z-axis, or like it's e to the minus j beta z. But for the cross section, we need to find the distribution, and there is multiple ways. Either like, so this is one way to have like more dense arrows. It means that the field is going from bottom up, and it is more density of arrows here. It means higher amplitude. Here it's less density of arrows, so it's less amplitude. Or we have like a curve to indicate, okay, here the electric field, tangential electric field, here it's in the y direction. So here it will be 0, here it will be 0 because it's the tangent to the conductor, and here it's peak. Also we can have like a color coded, so red is the highest, so we can do it this way. We can just draw the curve, we can just draw arrows, we can combine whatever makes it clear how it look like. we do it. So this is the transverse electric field 1 0. It just has this it has this distribution along the cross section. TE20 will have it here, 3 0, so on and so forth. The other mode of propagation inside a rectangular waveguide is the TM mode. We do like a similar procedure with the separation of variables, but we have here, we apply the same boundary condition, but also like the boundary condition, we have EZ is tangential for both y equal 0 and b and x equal 0 and a. So we have more boundary conditions here. To satisfy the boundary condition, we'll find that the solution for EZ does have this expression. From EZ we can derive EX, EY, HX, and HY. Same definition for the propagation constant. Same meaning for the cutoff frequency. The definition for wave impedance is the same that we discovered or just we discussed last lecture. But here, like, there is one major difference between TE modes and TM modes, is that there is no zeros in TM modes. So there is nothing called 0 0, 0 1, 1 0. All of those does not exist, because if M is 0 or N is 0, sign will be 0, so EZ will be 0, all the other will be 0. So for TM modes, the first mode in terms of like frequencies, the mode with lowest cutoff frequency is TM11, and we can see that TM11 and TE11 are degenerate modes. They have the same cutoff frequency, FC TM11, FC TE11 equal to one another. Both of them is having M equal 1. So TE11, TM11 are degenerate modes. So one assignment here for you. We need to calculate the losses due to conductor and dielectric for first mode in TE and first mode in TM in a rectangular waveguide. We're going to use the standard waveguide WR137. You can look up its dimension from the internet. The dimension is here. We need to compare the two curves against frequency. So of course you're going to do this calculation using MATLAB or something, so you need to submit the formula used for the calculation, the MATLAB routine, the plotted curve, and your comment and observation. You can use any reference. You can look up the formula you use from the book and program it on MATLAB, put the data and compare the two curves and comment on them. This is due in a week from the discussion session. Like in microwave circuits that is based on waveguides, many times we need to connect different sections of waveguides, and when we do this we use like flanges, like this one. It's called like cover flange, to connect the waveguides to one another. The flange need to be like very clean, accurate, leaving no separation between the waveguides, because if we have a separation and we are carrying high power on the waveguide, this separation can cause a breakdown. Breakdown means that the electric field at certain point is beyond the capacity or like the resistance of the dielectric material, and it can cause the dielectric material to break down, similar to what is happening in the sparking plugs in cars. So we increase the potential, and the separation between the two conductor on the spark plugs is short. So what happens, because of the presence of gas or the spray of benzene into like the environment or into this volume, we have like a breakdown, and there is a spark, then we have an explosion. This explosion later on is converted into motion. So here, if we have like small separation or like some voids in the interface between the two waveguide sections, we might have a very high electric field across a small distance, and this would cause a breakdown. The breakdown can cause like a system failure, of course. So like being accurate and clean and neat and would be unnecessary, especially if we are working with high power. This kind of discontinuity, we would expect very small standing wave ratio. Because of this, we are talking about like 1.03, very small effect. Sometimes when we have high power, we can't risk like having voids or like any irregularity or void like close to the interface because of the breakdown. So there is a different type of flange, which is choke flange. This part here is called choke flange. So sometimes, to avoid any possibility of breakdown, we connect cover flange to a choke flange. The choke flange is like this way. So we have some circular groove, and we have certain like distance. So how it works this way. So here, this distance here is lambda guide by 4, and this is short circuited here. So what we see here, we see open circuit. Like if we are looking into this direction, we see an open circuit here. Then this distance here also is lambda by 4. So when we are looking in this direction, we are seeing an open circuit, and we are lambda by 4 away from the open circuit. So we see a short circuit here. So the input impedance at the input of this gap looking in that direction would equal 0, which makes like this is like very low resistance. And this way we have a gap, but we make sure, because of this structure, that we have no or like very low electric field across the gap. So we are protected against choke or breakdown. Of course, because of this irregularity, the standing wave ratio for this kind of cover to choke flange interface is larger than cover to cover flange interface. So here it goes up to 1.05, still very low. The important thing, because lambda G is frequency dependent, this behavior of the choke is frequency dependent as well. So at the center frequency, we have like the perfect standing wave ratio, but if we are using it for a wide band application, then the standing wave ratio will increase at frequencies away from the center frequency. So other types of waveguides, we have the circular waveguide. Circular waveguide is also like a single conductor waveguide. It can carry TE or TM modes. It can't carry TEM. Its mass is different, so because it's based on Bessel function. We are not gonna study it, but it's very similar to what we had done. The main difference is like the use of Bessel function. So it's a different mass than the rectangular waveguide. The other waveguide is a coaxial waveguide. Coaxial waveguide also can be named transmission line waveguide, or like most of the time people say coaxial cable. The coaxial cable, because it has two conductors, it can carry TEM mode. So the main or the dominant mode for coaxial cable is the transverse electromagnetic. Again, because it's circular, it has like a Bessel function first type, second Bessel function second type. So it's a different mass, as I said. It's very widely used for transferring microwave and RF power between subsystems. The main thing is because of its flexible structure. So it can be like you see, of course, like coaxial cable. So because it's a cable and it can carry high power, it's used to transfer or like to connect different components in a flexible way. There is like more waveguides, like surface waveguide, similar to this one. If we have a ground plane and we have like a dielectric material covering this conductor, we can have a surface wave. Surface wave can be TE or TM. Of course, because it's a single conductor, we can't excite TEM waves. The surface wave are like known by a field that is decaying exponentially away from the dielectric interface. So if we are here, the field is decaying exponentially in this direction, but it is propagating in that direction. So there is like a large number of surface wave structure. This dielectric can cover a plane, it can cover a rod, it can be like a corrugated metallic conductor, so on and so forth. Then we come to the like a very widely used transmission line, or sometimes waveguides, whatever, however you would like to look at, is the PCB transmission line. It is used, as I said, because it's low profile, it's more convenient for connecting electronic components. And the main types are the microstrip, which is the trace that carries the signal over a reference plane separated by a dielectric material, or this is a buried or embedded microstrip. So one conductor over a reference plane, but it is immersed into a dielectric material. Strip line, a signal conductor between two reference planes, either symmetric in the middle vertical position between the two planes, or asymmetric one like this shape. We have also other types like coplanar waveguide. So we have coplanar waveguide with a reference plane. So we have ground signal, or ground signal, ground. So for transmission lines, most of the time we can either analyze or synthesize. For analysis, we just like take the dimensions, the physical properties of the material, and we need to calculate the velocities, the losses, impedance, and so on and so forth. Synthesize is that I give you certain requirement. I need this characteristic impedance, I need this amount of losses, I need this speed velocity. Then you like arrange them in a way to synthesize a waveguide. So there is many tools that can be used for this. For example, like you can use the transmission line calculator for QUCS, quite universal circuit simulator, and you can analyze and synthesize. There is many other tools, of course, and there is like online tools as well. For the strip line, we have like this is the signal trace, and we have two reference planes, and the separation between them is filled with a dielectric material. Because the strip line has two conductors, it can support TEM waves, and this is the usual mode of operation. Because it's like a parallel plate guide, strip line can also support higher order modes, even though the TEM mode is the dominant mode. And we can guarantee just a single mode by restricting the ground plane spacing and the side wall width, like how far it is from both sides, to be much less than lambda g. If we use small spacing and small widths, we guarantee no higher order modes. Microstrip line, actually it is like a single conductor, sorry, it's a double conductor, but in reality it can't carry TEM mode because it has some of the field, or a fewer percentage of the field propagating in air, and the majority of the field is propagating in the dielectric material. Because of the different phase velocity in air and in dielectric material, it can't support, theoretically speaking, it can't support transverse electromagnetic mode. But because in most of the applications, the separation here, the height is small, and the majority of the field is propagating in the dielectric material, we can assume like a quasi-static or quasi-TEM mode. Quasi-TEM mode is happening if the separation is much smaller than lambda, and we can do this sort of translation. For this structure here, this is the real structure, and this is the equivalent structure. In the equivalent structure, all the media is from a dielectric material with a dielectric constant called effective dielectric constant. The effective dielectric constant, of course, greater than 1, but it is less than epsilon r. The value of the effective dielectric constant depends on frequency, geometry, and physical properties of the material. So in reality, it depends on how much fields are existing in the dielectric material versus how much field exists in air. So this way, we can take this structure and do the analysis for this structure. This structure is sort of like TEM mode, and that's why we're saying this is quasi-TEM mode. The field here is close enough or approximately close to this one, so we can do the analysis on this one, which is much easier because we have a single dielectric material everywhere, which is easier than here. Of course, things would be more complicated when we go for higher frequency and when we have higher order modes. But again, thanks for the simulation packages that we are using, simulation package to do this analysis, like numerical techniques, and we don't do the analysis manually by our hands. Coaxial waveguides, we have many times we need to connect, for example, coaxial cable to a board, coaxial cable to another device, so on and so forth. So there is a large number of coaxial connectors that we're going to show shortly. But just quick comment about why 50 ohm is very common and very famous impedance for transmission line. This idea is coming from optimization of the transmission line dimensions, either optimization for minimum attenuation, minimum loss, or optimization for maximum power capacity. So for maximum power capacity, the ideal dimension for air-filled coaxial cable is 30 ohm. Minimum attenuation is around 77. So as a way of compromise in between to have like low enough losses and high enough power, 50 ohm was chosen in between. So those are different types of coaxial connectors. You have all the like N-type and PNC, and SMA is a very famous one, so on and so forth. Different ones has different advantage and disadvantage, so it's good to know their shapes. And we have like those for the very small one. Okay, so this is the end of this lecture. Just reminding that we'll have a homework and we have an assignment. Both of them are due a week from the discussion session. Thanks everybody, and meet you in the discussion session.